Hello and welcome back. Today we're recording from the Princeton University Chapel, where one of the people that we will study, Rafael Guastavino, contributed to its construction. We continue our cultural study of vaulted forms. We started with Germany, where the equations defining dome and barrel vaults were developed. Then we traveled to Italy to study the works of Pier Luigi Nervi. And now we examine Spain and their important historical contributions regarding vaulted construction. The goals for today's lecture are first to examine the tile vaulting tradition of Spain, and we will do this through the works of Rafael Guastavino and Antonio Gaudi. Second, we're going to look at some significant reinforced concrete vaults designed by Spanish engineers. In particular, we'll examine Eduardo Torroja and Félix Candela. Gustavino, Gaudi, Torroja, and Candela are all very important figures in the history of vaulted construction and architecture, not just for Spain, but globally. Each deserves their own lecture. However, due to time limitations for this course, I have decided to only briefly mention the work and importance of three of them and expand upon only Candela in the next lecture. I encourage the audience to read more about Gustavino, Gaudi, and Torroja through the many available publications. Last time we studied how Pier Luigi Nervi used hundreds or thousands of small prefabricated pieces to create his vaults. The Spanish have also used hundreds or thousands of small pieces to create vaults, but in a manner very different from Nervi. I'm referring to tile vaulting, also called Catalan vaulting. This is a tradition in Spain with its earliest known origins traced back to Valencia in the 14th century. Tile vaulting is a construction technique that uses several layers of tile to create the vault. In the first layer of tile, the tiles are connected on their edges with quick-setting plaster that holds the tile in place almost instantaneously. There is no need for support from below, which makes for fast and economical construction. An example of tile vaulting can be seen to the entrance to the National School of Ballet in Havana, Cuba. In this entrance, you see the layers of tile that create the vault. Rafael Guastavino y Moreno, born in 1842, is an important figure in this construction technique of tile vaulting. He was born in Valencia and studied master building and history and theory of fine arts. He was both a designer and a builder. In 1880, he moved to the United States with his youngest son, Rafael, who was 9 years old at the time, and he establishes the Guastavino Fireproof Construction Company. He comes to the United States with his young son, a dream, and some savings. He doesn't know how to speak English, but he has a talent for construction that transcends the language barrier. This construction method not only leads to efficient, economical, and elegant designs, but it also has one very important attribute for this time period, meaning the late 19th century. It is fireproof. To claim that his vaults were fireproof was an important marketing tactic, especially coming on the heels of the Great Chicago Fire of 1871. Guastavino actually did some fire tests on his vaults to prove to the building authorities that indeed the vaults do not collapse and continue to carry load after a fire. The project that was perhaps the most significant for making the Guastavino Fireproof Company known is the Boston Public Library. If you enter the library, you will see several tiled vaults designed by Guastavino. He went on to design several other structures in Boston. The Guastavinos, father and son, designed vaults in at least 30 states and 6 countries. But New York City is where he and his son left their greatest impact with over 200 structures designed there. Look, for example, at the structures under the 59th Street Bridge. There you will see again the tile vaults designed by Guastavino. If you enter Grand Central Station, you will also see Guastavino's designs. Enter the Oyster Bar and have lunch and look up at the tile vaulting there. That is what I did with some of my students and a colleague. After lecturing on Guastavino, we went to New York City and enjoyed lunch at the Oyster Bar. An advertisement that the Guastavino firm used illustrates many of their better-known American domes, the biggest one being St. John the Divine, shown on top of the advertisement. Also shown is the National Museum in DC, which is in the second row on the left. The fourth one down on the right is the University Library at NYU, and to the left of that is St. Paul's Chapel at Columbia University. Rafael Guastavino Sr. died in 1908, and his son, Rafael Guastavino Jr., took possession of the company. Guastavino Jr. designed St. John the Divine in 1909. It was the Guastavino's largest dome, measuring 135 feet or 41 meters across the diagonal of the square plan. By this time, Guastavino Jr. was using graphic statics to analyze the domes. Graphic statics is a structural analysis technique that you will learn about later on in this course. The same architect who designed St. John the Divine also designed the Princeton University Chapel in 1928 and worked with Guastavino again. The architect was Ralph Adams Cram. Even though the main vault in this chapel was not designed by the Guastavino company, some auxiliary domes not open to the public were built by them as indicated in the chapel drawings that are available in the archives at Princeton University. I recently spoke to a colleague of mine, John Oxendorf, who's a professor at MIT and currently the director of the American Academy in Rome. Dr. Oxendorf is also a scholar of Guastavino Vault and wrote an excellent book on the subject. When I met with him, I took the opportunity to ask him a few questions on camera.
Well, it's great to be here with you. I mean, this technique, I think, the whole world should know about. It's an 800-year-old construction method spread all over the Mediterranean. When Guastavino brings it to the US, here at the Boston Public Library, his first major building, he builds doubly curved, unreinforced brick shells that are only about 10 centimeters thick with huge load capacity. You can pile bricks 20 feet high on top of this, huge load capacity. And it's fireproof, so it catches the imagination of American architects. This is in 1889. And from there, they go on to do 1,000 buildings all across North America.
So why is it important for our audience to know about Guastavino and this kind of construction?
Well, it's a very important chapter in American architectural history. In the late 19th century, at times, thousands of buildings burned in a single fire. So, Great Fire of Chicago, 19,000 buildings burned. So architects were obsessed with keeping buildings safe and cities safe from fire. So it's a moment in American cultural history that's very important. Architecturally, we're trying to build grand public buildings that evoke the great cities of the world, because American cities are pretty young. And so we can't rival Rome or Paris or London, and or even Angkor Wat. And so American architects are trying to build grand buildings in brick and stone to show that we can rival the great cities of the world.
Wonderful. And why do you think that we don't build like this anymore?
Well, at the time, it was very cost-effective, strong, fireproof, and beautiful. It wasn't in the building code, but it got grandfathered in. Over time, we stopped building it because the cost of labor got high. This is quite intensive for labor, but I also think that's not necessarily a bad thing because you employ people to do the work. But also, architectural style changed. It became straight lines and modernism and not vaults. And we basically lost the ability to do it. We lost the technique.
That's a shame.
It is a shame.
So beautiful.
And our work today is trying to understand these great buildings, but also preserve them for the future. Because every year, vaults are either painted over, torn down, or a drop ceiling is put under them. And they're beautiful structures. So we're trying to raise public awareness and get people to the point where if you have a Guastavino ceiling in your building, it actually adds value to the building, and you should celebrate it.
And don't tear it down.
Don't tear it down. Understand it, marvel at its doubly curved, very strong structure as a shell, and its unique chapter in world architectural history.
Beautiful. Well, thank you for the work that you do and
Thank
for talking
you.
to us. There is so much more to learn about the Guastavinos. I highly recommend that you read more about their structures. And afterwards, if you have a chance, visit Guastavino vaults. It's an experience that leaves a lasting impression. Another Spaniard, also famous for his tile-vaulted structures, is Antonio Gaudi. Gaudi's legacy can be seen in Barcelona. Antonio Gaudi was born in 1852. He studied in la Escuela de Arquitectura in Barcelona, and he's famous for his rational structures, in other words, structure that generates form, and I'll explain what that means in a moment. In the 1880s, Gaudi began to do work for the Güell family, who became his patrons for many years. This image is the beginning of his design of a chapel for the Colonia Güell, which is a workers' settlement for the Güell's textile factories west of Barcelona. The, quote, rational idea of a string model is to load the strings in two directions with weights. Then one takes a photo of this model and turns it upside down. Then Gaudi makes a rendering of this upside-down drawing, which was drawn over top of the photo and represents the interior space. Next, he would drape some cloth over the model with hanging weights, took a photograph, again turned that photograph upside down, and from that, he would make a rendering of the chapel. The Güell family ran into some financial difficulties, and this chapel was not entirely built. Only the lower section was built. But the slender columns were designed to carry the forces of the church above that was never built. Another view of the columns shows the vaults. Gaudi uses tiles and stone for his constructions. Gaudi has said, quote, "Have you noticed that when a man uses a cane to walk, he inclines it? Well then, the inclined columns are stone canes." He plasters on these columns broken tiles so that it melds in with the trees. Gaudi says that his prototype was, quote, "this tree, which holds itself erect, which supports its branches and twigs and leaves. The tree does not need external support. Everything is balanced naturally. Everything is in perfect equilibrium." Gaudi is probably most famous for the expiatory church of the Holy Family, otherwise known as Sagrada Familia. What's important for this lecture in this church is the school roof just beside the large cathedral. This school roof is made out of a form called a conoid. A conoid has a series of straight line generators. In other words, you can form this doubly curved surface of the roof with one set of generators that are formed with straight lines. This property makes them easier to construct, especially in reinforced concrete, as Félix Candela will show later on. The original school roof, however, was not constructed with reinforced concrete, but with tile by means of tile vaulting. The original construction revealed the layers of tile on the roof overhang. And an inside view of the schoolhouse shows beams that were used to construct the roof and illustrate the conoidal form. One of our undergraduates, Barra Lane, did a research project on this structure in 2007. She wanted to learn if the roof, due to its double curvature, could support itself without the beams. So she did a finite element analysis of the roof. A finite element analysis is a computer model that predicts the forces on the roof. She looked at the stresses along the 3 pink strips. Her study found that the stresses on the roof were very similar, comparing the analysis with the beams and without the beams. In both cases, the stresses were very small compared to the assumed capacity of the tile material. So why did Gaudi leave in those beams? There are some ideas. Perhaps to emphasize the geometric form, or perhaps he just chose to ignore them after the construction was complete. Or maybe he wanted added strength. Maybe he didn't have confidence in his form. Remember, this was a time when we didn't have computers and the kind of tools we have available today to confirm our analysis and design. As Barra concluded, while the beams were originally used as linear elements that help guide the construction of the conoidal shape, the curvatures of the surface provided essentially all the strength once the roof was formed, and the beams merely stand as remnants of the formwork. In 2001, the schoolhouse was moved to another side of the Sagrada Familia to make room for the church's construction. In comparison to a photo taken in the 1960s, we see the form of the conoid is a little different. In addition, the new construction does not express the layered tiled construction nor the thinness. Unfortunately, it seems that the move of the schoolhouse deleted some of its authenticity from the original design. There are many books and publications on Gaudi, but in this lecture I discussed only the attributes related to structural form, as we saw with his hanging string and hanging cloth method, and with the conoidal form of the schoolhouse. Gaudi and Gustavino were not designing in the relatively modern material of reinforced concrete. To study exemplar Spanish vaults made of reinforced concrete, we need to examine Eduardo Torroja.